Welcome to AI News Digest 2026-06-16. Today's 10 stories. Story 1, OSGuard, a benchmark for safety in computer use agents. Story 2, PrologMCP, a standardized Prolog tool interface for LLM agents. Story 3, trust between AI agents, measuring formation, breakage, and recovery with implications for governing multi-agent systems. Story 4, metric match, a subset selection approach to evaluating LLM judge reliability. Story 5, a definition of good explanations and the challenges explaining LLM outputs. Story 6, Dr-DCI, scaling direct corpus interaction via dynamic workspace expansion. Story 7, CONCORD, asynchronous sparse aggregation for device cloud RAG under document isolation. Story 8, cognitive debt, AI as intellectual leverage and the dynamics of systemic fragility. Story 9, risk-aware LLM agents for geospatial data retrieval, design and preliminary adversarial evaluation. Story 10, relational structural causal models. Story 1, OSGuard, a benchmark for safety in computer use agents. A new paper from Columbia University's Causal AI Lab, accepted at the prestigious International Conference on Machine Learning in 2026, is making waves in the artificial intelligence research community. The work, by Adve and Elias Barenboim, introduces something called relational structural causal models, a framework designed to give AI systems the ability to reason causally in environments where objects and their relationships are constantly changing. To understand why this matters, consider what we want from a truly intelligent AI. We want it to understand not just what is happening in its environment, but why things happen, what would occur if we intervened, and how outcomes might have been different under different circumstances. That kind of reasoning, causal and counterfactual thinking, has been formalized for decades through the work of Judea Pearl, whose structural causal models have become a cornerstone of the field. But Pearl's classical framework has a limitation. It assumes a fixed set of variables, a fixed cast of characters. Real-world environments don't work that way. Traffic scenes have varying numbers of cars, pedestrians, and signals. Social networks add and lose members. Drug interactions involve different combinations of compounds in different patients. Ijaz and Barenboim tackle this head-on. Their first major finding is actually a negative one, a formal proof that without additional structural assumptions, you simply cannot answer causal or even basic observational questions about object combinations you haven't seen before. This isn't a failure of any particular algorithm. It's a mathematical impossibility. But the paper doesn't stop there. The authors define new tools called relational causal graphs and derive identification criteria, essentially formal rules for determining when and how causal effects can be reliably estimated, even when there are hidden confounding factors at play. They also propose a neural network implementation of the framework, called relational neural causal models, and show that it outperforms non-relational approaches on simulated traffic scenes involving varying combinations of cars, signals, and pedestrians. The implications here are substantial. Autonomous vehicles, robotic systems, and multi-agent AI all operate in exactly these kinds of variable relational environments. Any AI that needs to make decisions, not just predictions, in such settings will require the kind of causal generalization this framework enables. Beyond engineering applications, the framework offers new tools for causal inference in social science, epidemiology, and network analysis. This paper is likely to become a foundational reference for anyone working at the intersection of causal reasoning and relational AI. Story 2, PrologMCP, a standardized Prolog tool interface for LLM agents. Here is a question worth sitting with. What happens to your ability to think when you stop needing to? A new theoretical paper by researcher Shuchen Meng, posted to arXiv in June 2026, takes that question seriously and builds a formal economic model around it. The paper introduces the concept of cognitive debt, defined as the stock of unverified reasoning obligations that accumulates when people use AI to replace their own thinking rather than enhance it. The framework draws a deliberate parallel to financial debt. When you borrow money, you get short-term purchasing power in exchange for a long-term obligation. When you outsource your reasoning to an AI system without verifying or internalizing what it produces, you get short-term productivity in exchange for a long-term erosion of your cognitive capacity. And just like financial debt, cognitive debt can build up invisibly during good times until a crisis forces it into the open. The paper establishes 6 formal propositions. One of the most striking is what the author calls a cognitive Minsky moment, named after the economist Hyman Minsky, who showed that financial stability itself breeds instability. The idea is that when AI systems are working well and reliably, users lower their guard. They rely on AI more, verify AI outputs less, and their own reasoning skills atrophy. All of this happens while the true fragility of the system is actually increasing. Then something goes wrong, an AI failure, a novel situation outside the training distribution, a cyber attack. And the system collapses harder than anyone expected because the human backup capacity has quietly degraded. Even more unsettling is the prediction about high-skilled workers. The model shows that people who start with the most cognitive capital, the experts, the analysts, the highly educated, are actually most likely to adopt AI intensively because their returns are highest. But that intensive adoption also erodes their unaided abilities the fastest. Over time, the cognitive gap between experts and novices could actually shrink, not because novices improve, but because experts degrade. The policy implications are significant. Educational systems may need to mandate first principles reasoning even when AI shortcuts are available. Organizations may need to treat AI dependence as an operational risk, not just a productivity metric. And regulators may eventually need to think about cognitive leverage the way financial regulators think about balance sheet leverage. The paper is preliminary and theoretical, but it raises questions that the field urgently needs to grapple with. Story 3, Trust between AI agents. Measuring formation, breakage, and recovery with implications for governing multi-agent systems. Satellite data has never been more valuable. From tracking wildfires to monitoring crop yields to assessing hurricane damage, Earth observation imagery sits at the center of some of the most critical decisions being made today. The problem is that accessing this data typically requires specialized skills in geospatial information systems and remote sensing, expertise that most emergency responders, climate scientists, and policy analysts simply do not have. A new paper accepted for the ISPRS Congress 2026, authored by Kyle Gao and colleagues at the University of Waterloo, presents a framework designed to solve exactly that problem. The system uses large language models to let anyone retrieve satellite imagery and environmental datasets from cloud-based geospatial catalogs simply by describing what they need in plain English. The system then converts that natural language request into the precise, structured API calls needed to fetch the right data. The architecture uses 3 coordinated AI agents. The first, called General QA, interprets what the user actually means. The second, called Recommender Analyst, knows the technical schemas of specific geospatial data catalogs and generates the right API calls. The third, and arguably the most important, is the Guardrail agent. This agent sits at the intercept level, meaning it screens requests before they reach the other agents, specifically to catch adversarial inputs that could be used to manipulate the system into making unauthorized or dangerous API calls. This matters because the adversarial testing the researchers conducted revealed a real problem. When users craft multi-turn conversations designed to trick the system, prompt-level safety instructions help but do not fully close the gap. Rare but high-impact API manipulation failures still get through. The authors are transparent about this limitation and argue it is precisely why a dedicated system-level guardrail agent is necessary, rather than trusting the base language model's built-in safety training to do the job. The framework is designed to be portable. By swapping out the API schema, it can work with different geospatial data providers without redesigning the underlying architecture. That makes it a potentially versatile tool for environmental agencies, disaster response organizations, and climate research teams. The key remaining challenge is hardening it against adversarial manipulation before it can be trusted in high-stakes real-world deployments. Story 4, Metric Match, a subset selection approach to evaluating LLM judge reliability. Metric Match introduces a method to estimate the reliability of LLMs judge systems using only a limited number of human annotations, making judge evaluation more tractable and cost-effective. The approach selects a strategic subset of samples to maximize correlation estimate accuracy, directly addressing the bottleneck of expensive human labeling in evaluating generative AI outputs. This has strong practical implications for teams using LLM judges in production pipelines. Story 5. A definition of good explanations and the challenges explaining LLM outputs. This paper tackles the foundational question of what constitutes a good explanation for AI outputs, proposing a formal definition inspired by counterfactual reasoning. The authors identify specific challenges in applying this framework to LLM outputs, making it relevant to explainability and AI adoption in high-stakes domains. A rigorous definition of explainability is a prerequisite for building trustworthy AI systems. Story 6. Dr-DCI. Scaling direct corpus interaction via dynamic workspace expansion. Dr-DCI proposes a new paradigm for agentic search over large document corpora by enabling direct, shell-executable corpus operations rather than relying solely on retriever-mediated ranked results. This allows agents to reorganize material and verify cross-document constraints more effectively than traditional BM25 or Colbert-based pipelines. The dynamic workspace expansion mechanism makes the approach scalable for real-world agentic RAG applications. Story 7. CONCORD. Asynchronous Sparse Aggregation for Device Cloud RAG under Document Isolation. CONCORD addresses privacy-preserving RAG in device cloud collaborative inference settings, where private documents on edge devices cannot be shared with cloud-hosted models. The system uses asynchronous sparse aggregation to enable effective retrieval-augmented generation without raw document exchange. This is highly relevant as on-device LLM deployments grow and enterprise privacy requirements tighten. Story 8. Cognitive Debt. AI as Intellectual Leverage and the Dynamics of Systemic Fragility. This paper introduces a formal economic-style model of cognitive debt, the accumulation of unverified reasoning obligations when AI is used as a substitute for first principles thinking. The model treats cognitive capital as collateral and derives 6 formal propositions about systemic fragility as AI adoption scales. Unlike opinion pieces on this topic, this work provides a rigorous theoretical framework with falsifiable predictions. Story 9. Risk-aware LLM agents for geospatial data retrieval, design, and preliminary adversarial evaluation. This paper presents a multi-agent LLM framework for retrieving satellite imagery and environmental datasets from cloud geospatial catalogs using natural language queries. A 3-agent architecture, guardrail, general QA, recommender analyst, integrates safety enforcement directly into the pipeline. The adversarial evaluation component makes this relevant to both practical remote sensing applications and LLM agent safety research. Story 10. Relational Structural Causal Models. This work extends Perl's structural causal models to relational settings where objects and their relationships vary, enabling AI systems to reason about interventions and counterfactuals in combinatorial environments. The authors establish formal conditions for learning such models and prove generalization guarantees to unseen object combinations. This foundational research is relevant to building AI systems with robust causal reasoning and compositional generalization.